Should definitely get the tests back on Monday. Um, and so let's wait to talk about the tests until then. Um, I just want to today get back into pulling forces, cable forces. Um, so back to pulling force, and we're talking about cables. Uh, Even if there's no cable involved, you can always think of a pulling force as being applied by a cable, and you can always do the problem that way. But the new thing that I want to introduce today is cables that pass through um, massless, frictionless pulleys. Um, that might seem like a lot to assume about a pulley, but in a lot of applications, the performance of a pulley is always best if it's for massless and frictionless. And so in a lot of applications, you're trying to sort of get to this to a place where the mass and the friction are very small compared to the other forces you're using. So this gives good results a lot of times. Um, and the key idea is that all a pulley does is change the direction of force. So we're not talking about a change in the magnitude. We're only talking about a change in the direction of force the cable applies to connected objects. Um, and because of this, if you have two objects that are connected to the same cable, but that cable passes through a pulley, a lot of times one of the key things you're going to have to do is figure out a relationship between the motions of the two objects. You know, if you just have two boxes that are sliding along a ramp or a surface, okay, then they're both going to have the same. You know, you move this one an inch that way, this one has to also go an inch that way. And because of that, if this one has an acceleration of a that way, this one has an acceleration of a that way. But now let's think about, so the first example I'm going to do is one like this, where you have a pulley connected to the ceiling and two objects connected like this. Let's say that one's 5 kilograms and that one's 10 kilograms. And now those are not going to have the same acceleration. Um, but geometrically, there is a relationship between them. So what's going to happen is, um, this is a pretty easy one to have intuition about. The 10 kilogram box is going to accelerate down, and the 5 kilogram is going to accelerate up. Okay, so you can't think of like a single acceleration vector for both of them. So notice um, in problems like the one above, where two objects are connected to the same cable, and the cable passes through pulleys. Um, you'll need to find or let's say you'll need to know, it isn't something you'll calculate. You'll have to do this intuitively. You'll need to know the relationship between the motion of one object and the motion of the other object. Um, in the example above, uh, whatever the acceleration of the 5 kilogram box is up, that's going to be the downward acceleration of the 10 kilogram box. To figure out that relationship, this is the way I like to think about it. So here's a good way to think about it. Um, if one object, I was going to say box, one object is an inch in the positive direction, how does the other object have to move? Yeah, that's true in this case. And so, exactly. And so you have that. Um, so that relationship, if you just think about a change in the position of 1 inch or 1 meter or whatever, is the same as the relationship between the accelerations. Um, so that gives the relationships between the accelerations. It also gives the relationship between the velocities, but those aren't as important to us because acceleration is what we use in Newton's laws. Okay, so I'm just going to do 2 examples. Anybody have any questions before I do these? Okay, so first I'm going to do the one I drew above. So we have a 5 kilogram mass and a 10 kilogram mass. And we want to figure out the acceleration of one box or the other. Let's say we want to figure out the acceleration vector of first the 5 kilogram and second the 10 kilogram. So the way I'm going to do this is I'm going to start out by drawing free body diagrams of these 2 objects independently of each other. We're going to come up with a system of equations. And once we have our system of equations, we're going to see we have too many variables to solve, which means we're going to need another equation. That other equation is going to be the relationship between those accelerations. Okay, so free body diagram of, I'll start with the 5 kilogram box. What forces are acting? That's right. Yeah, gravity in the cable. So we have 5 kilograms times 9.81. Yep. So we have the weight going down and then the tension going up because cable force is always parallel to the cable, away from the body. So I'll call that T. And now I'll write out Newton's second law. So 0t plus 0, negative 49.05 is equal to the mass. And now, what do we know about the acceleration? So we know that we don't have to figure out what direction it's going yet. We'll think about that at the end if needed. It will be needed. But for now, we just need to know the acceleration. All the motion is going to be in the y, parallel to the y-axis, vertical. So I'm going to write this as 0, and this variable I'll call a5. Okay. The x equation doesn't give us anything, but the y equation says I'll write it as t minus 5a5 is equal to 49.05. Can we solve that for t or a5? No, one equation for two variables, so I'm just going to call that equation star and set it aside. And now we'll go on to the second body. And what forces are acting on the 10 kilogram box? Same, yeah. This time it's 10 times 9.81, so the force down is 98.1. It's the same cable, just going through pulleys, and so the magnitude of the force is the same. It's parallel to the cable, away from the body, so it looks like that. And then Newton's second law says 0t plus 0, negative 98.1 is equal to the mass times the acceleration of this one. What do we know about the direction of acceleration of this one? It is going down, but let's not even worry about that yet. We'll worry about that if we need to, okay? So for now, we're just going to say that's also moving vertically, and I'm going to call this 0, A10. Okay? The x equation doesn't give us anything. The y equation says t minus 10a10 is equal to 98.1. We can't solve that one. I'll call that 2 star. So now we have this system of two equations, the 2 starred equations. Can we solve those for the variables? No, because the a's are different. So we have star and 2 star are two equations for 3 variables. So we can't solve that. And so the last thing we're going to need is a relationship between A5 and A10. Find a relationship between A5 and A10. Okay. Well, so this is where we use that idea that I was talking about. Think about moving an inch in the positive direction. What does the other one do? All right, so let's say that let's say that a 5 kilogram mass moves an inch up. What happens to the 10 kilogram mass? Moves an inch down. So the relationship is 1 to 1 and just opposite signs. Okay, so we can write that as, I guess, if the 5 kilogram moves, 1 unit up, 10 kilogram moves 1 unit down. So our third equation just says A5 is equal to negative A10. And I'll call that our equation 3 star. And now we have three equations for three variables. I'm going to plug 3 star in to eliminate A10. So let's see what we have. We have a first equation that says T minus 5A5 is equal to 49.05. Now I'll plug 3 star into the second equation, and we get T plus 10A5 is equal to 98.1. Doesn't make any difference. You could think of all, even though in this example, we know from looking at it that the A is going to go up, that 5 is going to go up and 10 is going to go down. If you thought about it as what would happen if 10 goes up and the 5 goes down, you get the same relationship. All you're trying to do is figure out what the relationship is that's required by the fact that that cable stays the same length. Okay, so to solve this, let's go, let's take the negative of this one and add these two equations together. You can solve it however you want. It's just a system of equations. And you get the t's cancel out. 15A5 is equal to 49.05. And so you get A5 is equal to 3. Is that 27? I feel like I've seen these numbers before. Can someone divide that and see if it seems about right? Okay. Now, the last thing, since we were asked specifically for the acceleration vectors, now all we have to do is plug these values back into the vectors. For part A, we're looking for the acceleration vector of the 5. We'll plug 3.27 back into this acceleration vector, okay, that we used in Newton's second law, and we get 0 for x, positive 3.27 for y. And so that's the acceleration vector of the 5 kilogram. And then second, remember the variable A10 is negative A5, so that's negative 3.27. Plug that into our equation from Newton's second law for A10. And you get that the acceleration vector of the 10 is 0, negative 3.27. 0, positive 3.27. Any questions about that? Yeah, exactly. Every one of them is going to be that way. So let me do another example with the cable just passing over one pulley. So this time, let's say that there's a ledge, and the pulley's on the corner. Um, and the cable connects this cart to a hanging mass. Let's say the hanging mass is 2 kilograms, the cart is 10 kilograms. The acceleration of the cart. By the way, we didn't calculate the cable tension in the last problem or any forces just because the problem didn't ask for it, and I guess it doesn't ask for it here either. But when you solve that system of equations, you can solve for T also. So that's, a lot of these questions will also ask you to calculate the force, and you do it the same way. Okay, so I'm going to take the same 2 steps. I'm going to isolate the 2 bodies. We're going to see that we have a system we can't solve by itself, and then I'm going to use what we know about the motions of these objects. We can think of that as a geometric constraint equation. Just the geometry tells us how they move relative to each other. Okay, so a free body diagram of the 10. Forces act. Yep, so we have a 98.1 is the weight force. We have normal force pushing up from the ground, so I'll call that fancy N. And then we have the cable force this way. And then Newton's second law says 0, negative 98.1, plus 0, N, plus positive T, 0, is equal to the mass of the cart times its acceleration vector. And what's the direction of acceleration of this cart? What's the axis it moves along? Yeah, X, and in this stage, we don't have to choose a direction. That'll come out in the math. So we'll just always call it positive X or positive Y for now. I'm going to call this A10 for the X component, 0 for the Y component. We're only looking for these accelerations. And so it wouldn't hurt to write out the Y equation, but it turns out that's just sort of a unnecessary equation for an unnecessary variable. We might as well just leave it aside. Okay. It wouldn't send you down a dead end or anything if you wrote it in there. It would just be one more equation, one more variable. That's fine. Yeah, really, technically it is. That's not the kind of thing I would take points off for, but you know the direction of a force. And what you'd want to think of is the arrow shows you the direction, and all the variable does is give you the magnitude. That's why these are all just numbers. Okay. So, yeah, a lot of people, so yeah, little by little, we'll try to iron that kind of stuff out. But yeah, think of it as this vector is defined by a direction and a magnitude. Okay, so the X equation says 0 plus 0 plus T is equal to 10A10. I'll rewrite it as T minus 10A10 is equal to 0. Can we solve that equation? Nope, 2 variables. I'll call that star. And then we'll isolate the hanging mass. there's a weight force of 2 times 9.81, so 19.62 down. And then there's the cable force. What's the magnitude of that? T, it's the same cable, yep. Even though now it's in a different direction because of the pulley. And Newton's second law says 0, negative 19.62 plus 0 positive t is equal to the mass, 2. And what axis does this object move along? The y-axis. So I'm going to write this as 2 times 0 a2. Now in this one, it's easy to see the x equation doesn't give us anything. The y equation gives us 19.62 plus t is equal to 2a2. And I'll rewrite that as t minus 2a2 is equal to positive 19.62. And I'll call that 2 star. So now can we solve for the system star and 2 star? No. We have 3 variables, 2 equations. So 2 equations, 3 variables. And so now we have to come up with a relationship between those accelerations. If the cart moves an inch in the positive x direction, where does the hanging mass go? An inch in the negative y, exactly. And so we're going to say and notice we already have these variables A10 and A2 representing x motion and a y motion. So all we have to do is deal with that negative sign. And so again, we have the same thing we did before. We can say it as A2 is equal to negative A10. That's right, it doesn't matter. The reason it doesn't matter is we're doing it all as vectors. That gets a little bit obscured because A2 and A10 are just variables. What we've really done is said if we have an acceleration vector A10, 0 for the cart, we have an acceleration vector of 0, negative A10 for the hanging mass. We've done it all. We've dealt with all those differences in direction with the vectors. And by the way, if you do a problem like this and you see the relationship coming ahead of time, which you will in a lot of cases, you could just start out by writing that the acceleration of this one is going to be 0. The acceleration of this one is going to be 0, negative 8. Skip the whole constraint thing at the end. It's basically substituting in the constraint before you get there. But I think this is a nice sort of systematic way to think about it. Okay, now I'm going to write out this system of equations. This is 3 equations. For 3 variables. So the first one says t minus 10a10 is equal to 0. The second one, I'm going to substitute in this equation called 2 star, but this should be 3 star. I'm going to substitute that into equation 2 star. So we have t plus 2A10 is equal to 19.62. No, that doesn't matter. Think of it this way, like we use the vector equations to come up with just mathematical equations that we know are true. Okay. And then what you have is a set of equations, you know they're all true, and that means you solve them as a regular system of equations. It doesn't matter anymore where they came from, as long as as long as they're right, it doesn't matter where they came from anymore. Okay, so I guess again, I'll take the negative of the first equation, add these together, and you get that 12A10 is equal to 19.62. So you get for A10, 2.45. 635. 1.635. I guess it has to be less than 2, doesn't it? Bless you. And so now to get the final answer for the acceleration vector, just plug that value of A10 back into this acceleration vector. This is the answer that we're looking for. We just didn't have the number yet. Now we can put the number in. And so you get that the acceleration of the 10 kilogram cart is 1.6350. Any questions about that? All right. So that's how you deal with pulleys. Now I have a question. Has anybody heard of pulley advantage? You ever heard that term before? Um, exactly. Okay, so that's pulley advantage. But notice that that sort of seems to contradict what I said about pulleys so far. And I remember talking about this when I first saw pulleys in physics and being confused because I had sort of this vague idea that like pulleys could reduce the force required to lift something up. But then you see what a pulley really does, and all it does is change the direction of the force. The magnitude isn't changed. So I want to do an example to try to just sort of clarify how those really aren't contradictory. Okay, so pulley advantage. Um, there are ways to configure, so you can configure systems of pulleys so that the force required to lift a mass is reduced. And so I'm going to do an example very similar to the first one I did. Okay, I'm going to do an example like this one where we have a 10 and a 5. Okay, but it's not just going to be a single pulley like this. It's going to be a system of 2 pulleys rigged up in a very specific way. And what we're going to see is that we can use this system of pulleys so that the 5 kilogram mass holds up the 10 kilogram mass. Really cool how it works. It doesn't really seem possible, but we'll see mathematically that it works. And if you want to see it in lab, it doesn't take long to rig up a pulley system that where you can actually feel the difference. Okay, so what we're going to do is, so we're still going to have the ceiling. And we're still going to have a pulley attached to the ceiling. But then we're going to have another pulley that is not connected to the ceiling. It only holds up the mass. So here's the 10 kilogram mass. And then the cable goes through this whole system. And here's the 5 kilogram mass. And what we're going to see is that, I mean, just there's nothing about this system that makes no acceleration happen. It's just that these are exactly ratio of masses that makes this happen to be exactly at rest. But we're going to see that unlike the case before where the 5 kilogram mass accelerated upwards, in this case, they're in equilibrium. They're both just going to sit there. Okay. First, I'll do a free body diagram of the 5 kilogram. So that has a weight force down of 49.05 and a cable force T up. And so Newton's second law says 0T plus 0, negative 49.05 equals 5 times the acceleration that I'll just call A, 0A5. And that gives us our first equation. So T minus 5A5 is equal to 49.05. Call that star. And now I'm going to do a free body diagram of the 10, and this is the one that's going to look sort of odd. I'm going to isolate the 10 kilogram mass and everything that's hanging. So there's this, and then there's the pulley. And intuitively, I'm going to think of also including the part of the cable that goes under the bottom of the pulley. You see what I'm trying to draw there? Try it sort of like Batman. So now what's acting on this? There's a weight force down, 98.1. And there are cable forces applied by the cable that's not in our system to the cable that is included in our system. And that happens at two different spots. So we have a cable force here and a cable force here. That's all the same cable, so those forces have to be the same. Anyone have any questions about that? And Newton's second law then says 0T plus 0T plus 0, negative 98.1 is equal to the mass times the acceleration vector of this one. And this so it's just going to be moving vertically. So I'll call this 0, A10. And this gives us our second equation, 2t minus 10a10 is equal to 98.1. Nope, they're both in the positive y direction. So they add. Yeah. Yes. Yeah. We're isolating the 10 plus this thing plus the pulley plus the cable that goes under the pulley, that little stretch of cable under the pulley. And you know, if you get confused about the direction of those cable forces, just remember the rules for a pulling force. It's parallel to the cable, away from the chosen body, and so it has to be up in both of those two cases. Oh, we have the same thing that we had in the past couple. We have two equations for three variables. So we're going to need to come up with that geometric relationship between the motions. And this one is a little funny. So what happens now in this case if you let this go up an inch? You know, in the cases we've dealt with before, the other one goes down an inch. But think of it this way. These lengths have to have a certain relationship, right? The cable length between here and here and between here and here. Otherwise, one of those two sides would go slack. You know what I mean? So in order to lift this up, I guess in this case, to pull it down an inch, okay, you have to add an inch to the cable over here and add an inch to the cable over here. And that adds up to 2 inches. So in other words, if you if you pull this down an inch, the only way to do that is to lift this up 2 inches. Okay. And so the relationship here is that A5 is equal to negative 2A10. And now we have 3 equations for 3 variables. And so we have T minus 5A5 is equal to 49.05. And the second one I'll sub in for A10. So we have 2T plus 20A5 is equal to 98.1. I'm going to multiply that first equation by negative 2. Then we have negative 2T plus 10A5 did I do this right? A5 no, I did not do that right. So So A10 is equal to half of A5. So all right, so what am I doing here? So the second equation here should be positive 5.
Why is it positive 5?
Okay, so A10 is equal to negative 1/2 A5. Okay, and so then substitute in for A10. And if I'll just solve for t to start with, this gives us 3t is equal to 147.15. And so what do you get for t? Okay, 49.05. And now we'll plug that into any one of these other equations we have to solve for A5. We'll just probably want to use the easiest one we have. So I guess so now we have 49.05 minus 5A5 is equal to 49.05. Those cancel, and so A5 is equal to 0. So that 5 kilogram mass is holding up the 10 kilogram mass. Yes. I added these two equations together. So 3t, these cancel, and those when you add them together is 147.15. Tristan, did you have a question?
Well, the reason why it is A5 equal to -2 and A, because we're pulling like in these inches, right? Because we're pulling like
Right.
2 inches.
Well, I mean, not at least 2 inches. It's just that every unit of motion of the big mass, the 10 kilogram mass, requires 2 units of motion in the other direction of the 5 kilogram. And that's where that relationship comes from. Yeah, it's just totally because of the geometry of how that works. So pulley advantage allowed the 5 kilogram mass to hold up the 10 kilogram mass. Yes. The way to think about it is there's always going to be like a hanging section, okay? And you're always going to do a free body diagram of all the stuff that's hanging. And so if you have pulley, 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 which you can do the whole system of pulleys, you count up all of the cables connecting the hanging thing. In this case, it's 2, 1, 2. I mean, it's a single cable, but 2 places where it holds it up. And that's what you have to divide the acceleration by to get the acceleration in this one. Which, by the way, we haven't talked about conservation of energy yet. But an idea like this makes you think like, are you getting energy for free out of this system? And you're not, because even though the force is smaller here, you have to pull, this side has to pull down twice as far to make this go up one bit as far.
It's like it's stretching out.
Yeah, exactly. Right. It's the same effect as changing to a lower gear on a bicycle. you know. You have to go a lot more. The force you have to apply to the pedals is a lot lower, but you have to do a lot more revolutions of the pedals. See you tomorrow. Yep.
Not to your voice, I'm just curious.
I don't know. Just a cold, I guess. Hopefully it'll come back sometime.
So it sounds like this.
Yeah.
I want this to actually continue to program.
Yeah.
We have to figure out the force pressure on the 8 on we assume that because of
You can't assume that. So what you have to do is isolate all of them together and calculate the acceleration, and then isolate the 10.
Yeah.
And you don't know what that force is, just call it R.
Right.
And now you know the acceleration, and you can solve for that R.
So you don't. So 50 just completely
50
goes away
won't.
in that case.
Right. When you isolate this, there's no 50. But the way that it sort of sneaks in there is through the acceleration.
Okay.
Exactly.
So when do you want to create the test?
They'll be done Monday, I think.
Okay. So this quiz on Monday, right? Yes. One. Okay.
Okay.
Thank you.
Hi. Oh yeah, sure. Tomorrow would be great. Yeah. In the testing center. Doesn't matter to me. I'll just put it in the testing center today for tomorrow, and you can take it during their hours. Okay. Yeah, bye. Yeah. Oh, I haven't. How long ago was that? Are the notes up, but not the video? Look and see if the notes are up. I think there might have been a day where I think it was a day that all I did was work on problems, but I think there was a day where I didn't have a video, like the file didn't work. Okay. Yep.